I welcome the second speaker of the day, Apurba Biswas, who is going to talk about Mpemba effect in driven granular gases. And I hope I got the pronunciation of the first word
Yeah,
right.
yeah.
So yeah, welcome Apurba.
Hi everyone. I'll be talking about Mpemba effect in driven granular gases. So I will explain what is Mpemba effect and what are the known results in various physical systems and how to analyze this effect, especially in the case of driven granular gases. So this work has been done with Professor R. Rajesh along with Prasad and Oren. So let us consider this plot where temperature is plotted as a function of time. And now we consider two systems P and Q, where P is initially at a higher temperature than Q. And now if we quench both the systems uh, to a common equilibrium state where the final equilibrium state has a lower temperature compared to the initial conditions, then we see that the system P, which was initially at a higher temperature, relaxes to the final equilibrium state faster than Q. So this effect is known as the Mpemba effect. And this anomalous relaxation in temperature is different from the known Newton's cooling law, which is a quasi-static cooling. So if we consider the lower half of this plot, so this red trajectory shows the quasi-static locus. And now if we consider two systems, one at a higher temperature TH and another at a colder temperature TC, and now if they evolve quasi-statically to a final equilibrium state having temperature TB, then their trajectories won't cross and we won't be able to see the Mpemba effect. So it tells that Mpemba effect is essentially a non-equilibrium process. So now, starting from those two initial conditions, if they start to evolve along the trajectory shown by the purple and the yellow one, then we can see that the hotter system can cool faster than the colder one. So here are a few examples of Mpemba effect seen in various systems. So first example is that of water. So various reasons are known for the existence of such an effect in water, which includes evaporation, uh, supercooling, and hydrogen bonding. But they are specific to this system only, and they, and in general they do not define such effects in other systems. So here uh, the Mpemba effect is measured in terms of the time it takes to cool the initial temperature to the freezing temperature of water. So existence of such an effect in the case of water involves a phase transition, but we'll see that in order to define such an effect in other systems, it did not involve a phase transition. And also the quantity that is monitored here as a function of time is temperature, but it can be different for different systems. Like the second case, here the Mpemba effect is observed in magnetoresistance alloys, but here the analogous quantity to the temperature here is magnetization. So here the system which has a higher initial magnetization relaxes to a final equilibrium state faster than other initial conditions. And similar effect is observed in clathrate hydrates also, where we can see that if the initial temperature is higher, then it takes lower times to freeze. So in theoretical models, uh, Mpemba effect has been analyzed, which where the system undergoes Markovian dynamics. For example, in Ising model, three-state system, and in Fokker-Planck dynamics. But here the quantity that is monitored as a function of time is a distance from equilibrium function. So if we consider this plot, so here y-axis measures the distance from equilibrium of the various initial conditions. So here the trajectory shown by the red starts at a higher temperature and is initially at a larger distance from the equilibrium than the blue curve. But as it evolves in time, we can see that the red trajectory relaxes faster compared to the blue curve. And due to the presence of the Mpemba effect, various other interesting results are also observed, which involves exponentially faster cooling and also the result that if there is a pre-cooling stage in the system, then it can lead to faster heating. And recently, such an anomalous effect has been observed in experiments also for colloidal systems which are immersed in water, and the water acts as a heat bath for the system. So the experimental results suggest the existence of exponentially faster cooling for certain initial conditions. So here in these plots, y-axis is the distance from equilibrium, which is measured as a function of time. And for certain initial condition, like if we consider case 3, where the red trajectory is for the system which is initiated at a higher temperature, and the blue one is initiated at a comparatively lower temperature. And this is a semi-log plot. So the straight line for the red curve shows that it decays exponentially with a larger relaxation rate, whereas the blue curve decays asymptotically with a slower relaxation rate. Thus, it verifies the theoretical prediction made in the context of Markovian Mpemba effect. So such an anomalous effect has been observed in the context of driven granular gases also. So in this talk, we will look at various models of such non-equilibrium systems and how the effect can be analyzed. So let us first define the model for granular gas. So it is basically a dilute composition of macroscopic inelastic particles. So here the particles interact through binary collisions, and the collisions are momentum conserving, but due to the presence of inelasticity in the system, they dissipate energy. So these particles are supplied energy from external sources, and due to the interplay of this dissipation and the external supply of energy, they reaches a non-equilibrium steady state. Now, in order to analyze the Mpemba effect in such non-equilibrium systems, we define the granular temperature as the mean kinetic energy of the system, which is defined by this expression. And we will see in the various models that we will consider that the time evolution when calculated as a function, it will form a coupled differential equation with various other quantities. Like the first example as shown on the left, here the temperature T couples with the quantity A2. We will define these terms later when we consider the models. And the expressions on the right, here the temperature couples with another parameter theta. And we'll see that due to the presence of this coupling of the temperature T with other parameters, it ultimately leads to the existence of the Mpemba effect. So let's first consider the case of smooth granular gas. So in this model, we consider only the translational motion of the particles. So here, the translational kinetic energy is calculated as a function of time. And in this analysis, the velocity distribution function is approximated around Gaussian using Sonin polynomials. And this distribution function is put into the Boltzmann-Fokker-Planck equation, and the time evolution is calculated. And we see that the temperature T, which is nothing but the mean kinetic energies of the particles, couples with the parameter A2. So A2 is the excess kurtosis, or it is defined as the scaled fourth moment of the velocity distribution function. So the temperature T couples with A2 in this case, and let's see how it leads to the existence of Mpemba effect. So in this plot, the y-axis shows the temperature, which is plotted as a function of time. So let's first consider the first three plots on the upper half of this plot. And those three trajectories correspond to three different initial conditions for the temperature T and the parameter A2. So we can see that the blue curve, which is initiated at a higher temperature, relaxes faster compared to other initial conditions, which were initially closer to the final equilibrium state. And the lower half of this plot shows the existence of inverse Mpemba effect, where the system is heated instead of being cooled. So in that case, the red curve, which was initially at the lowest temperature, heats up faster than other initial conditions. But in this analysis, the velocity distribution, which correspond to the initial conditions of T and A2, are sampled from a non-equilibrium distribution, and it is not known how is their dependence on the intrinsic parameters of the system, so that they can be tuned to access these initial conditions. So we will try to answer these questions in various other models for driven granular gas. So next we consider the case of rough granular gas. So here we consider both the translational and rotational degrees of freedom. So we can define both translational and rotational kinetic energies, and their sum gives us the total kinetic energy, or we will define it as the granular temperature. We can define another quantity theta, which is the ratio of the rotational to the translational kinetic energies. And in order to obtain the time evolution of the granular temperature, here we use a Gaussian approximation for the velocity distribution, and we put it in the Boltzmann-Fokker-Planck equation for the velocity distribution. And we see that the granular temperature T forms a coupled differential equation with theta. And let's see how it leads to the Mpemba effect. So here in this plot, y-axis measures the temperature as a function of time, and the three different trajectories correspond to three different initial conditions of the quantities T and theta. And the blue curve, which was initiated at a higher temperature, relaxes to final equilibrium state faster compared to other initial conditions. But again here, the initial conditions were not sampled from a steady state distribution. So we do not know what are the system parameters that govern these initial conditions. So here we present an exact analysis for the existence of the Mpemba effect in the context of inelastic gases, and we ask the question if these anomalous effects are true if we consider the steady initial conditions to be true steady states of the system, and what are the system parameters that govern these initial conditions. So here is the collision model that we consider. So here the particles collide at a rate which is independent of the relative velocities of the particles. So this is sort of a stochastic model of collisions, and the collisions are obviously momentum conserving, but due to the presence of inelasticity, they dissipate energy. And in order to compensate for the loss of energy, the particles are driven at a rate lambda d. Here we model the driving as such by this form. This is a microscopic form of driving where Rw, the parameter Rw signifies the decrease in velocity when the particles collide with the boundary, and eta is a noise that is added to the velocities. And this eta, we do not use any approximation for the noise distribution, and it can be taken from any arbitrary distribution with a finite second order moment. So in this model is called a Maxwell model, and in this model we'll consider two different cases. One is the mono-dispersed gas, where we consider only one type of particles, and the other is the bi-dispersed gas, where two different types of particles constitute the system. And we will try to analyze the nature of the initial conditions for the existence of the Mpemba effect in both the cases. So let's first consider the case of mono-dispersed gas. So it consists of only one type of particles. So here the granular temperature is equivalent to the mean kinetic energy of the particles, and the exact analysis shows that the mean kinetic energy forms a closed coupled differential equation with the 2-point interparticle velocity correlation, C, which is defined by this expression. And we analyze this coupled differential equations between E and C to analyze the existence of the Mpemba effect. Let's first define the Mpemba effect in this system. So suppose we consider two systems P and Q with these initial conditions for E and C, such that system P is initially at a higher temperature than Q. So the criterion for the existence of Mpemba effect is that after a finite time tau, the trajectory for the P, which was initially higher than Q, will remain below than that of Q after the crossing time. So with this criteria, we can derive the condition for the existence of the Mpemba effect in terms of the quantities E and C, and they are related to the system parameters, which are included in these terms lambda plus R11 and R12. So based on this condition, we choose a pair of initial conditions for the systems P and Q, such that P is initially at a higher temperature than Q. So here y-axis is the energy plotted as a function of time, and we can see that the initial condition for P, which was initially at a higher temperature, relaxes faster compared to Q. But in this analysis, we see that only non-stationary states can give rise to Mpemba effect. So we consider this case for bi-dispersed case, and we will see that benefit of using this model is that we can choose steady state initial conditions, and we'll see how the initial conditions are governed by the intrinsic parameters of the system. And so here it consists of two different types of particles, A and B, and both the particles are driven with different driving strengths. And in the steady state, the calculations show that all the interparticle velocity correlations between the particles goes to 0, and we get different steady state energies for the particles A and B. So here the total kinetic energy, or equivalently the granular temperature, is the sum of the kinetic energies of A and B, and it forms a coupled differential equation with the quantity E difference, which is the difference between the kinetic energies of A and B. So based on the criterion for the existence of Mpemba effect in the system that we just discussed, we can derive this condition for this model, where the initial conditions are related to the intrinsic parameters of the system. So based on this condition, we choose a pair of initial condition that shows the existence of Mpemba effect, also the inverse Mpemba effect. Here the system is heated instead of being cooled, and the system Q, which was initially at a lower temperature, heats up faster than system P. And here is the phase diagram for the initial conditions, which are measured as a function of the parameter RAB. So RAB is the coefficient of restitution between A and B type collisions, and this solid line gives the critical line which is obtained from this condition, and all the initial conditions, phase space initial conditions that lies below this critical line shows the Mpemba effect, whereas the other region doesn't. And we can show that all the initial conditions can be generated by simply tuning the driving strengths that were defined for A and B type particles. So here we show that even steady state initial conditions, which can be controlled by tuning the system parameters, give rise to the existence of Mpemba effect. So here we present the possibility of the existence of strong Mpemba effect in this system, and strong Mpemba effect refers to the phenomenon where an initially hotter system, when quenched to the final temperature, relaxes at an exponentially faster rate. So if the time evolution is given by this expression, where it decays with different rates, lambda plus and lambda minus, and lambda plus is greater than lambda minus. And now if we set the coefficient k minus, which is associated with the slower relaxation rate, to 0, then we get the condition for the existence of strong Mpemba effect. So based on that condition, we choose the initial condition for the system P, which was initially at a higher temperature, whereas system Q doesn't satisfy the condition for the strong Mpemba effect. So in this plot, this is a semi-log plot where energy is plotted as a function of time, and we can see that the system P, which was initially at a higher temperature, relaxes exponentially with a single largest rate, whereas system Q decays asymptotically with the slowest relaxation rate as the time increases. Thus, bi-dispersed gas is a good candidate to observe the existence of Mpemba effect starting from steady-state initial conditions. So till now, we had considered a simple collision model where the particles were colliding at a rate which was independent of the velocities of the particles. So here we present a model for realistic collisions where the particles collide at a rate which is dependent on velocities, and here we show that merely a presence of anisotropy in the velocity distribution of the particles can lead to the existence of the Mpemba effect. So here is the model. Here we consider hard disks in 2 dimensions. So here particles collide at a rate which is dependent on the velocities, and obviously the collisions are momentum conserving, but they dissipate energy. So we apply noise to the velocities in order to compensate for the loss of energy. So here the driving is diffusive, which is a special case of the form of driving that we considered for the Maxwell model. The noise is Gaussian white noise. Here Zi0 square is the strength of the noise. Now, how do we introduce anisotropy in the distribution? So for that, we apply different driving strengths along the x and y directions of the plane, and we find that it gives rise to different steady-state kinetic energies along x and y. Now, in order to analyze the time evolution of these kinetic energies along x and y, we use an anisotropic Gaussian form for the velocity distribution, having different variance along x and y, and we put this form in the Boltzmann-Fokker-Planck equation for the velocity distribution of the particles. Now, since we get a different values for the kinetic energies along x and y, we define the total energy as sum of these quantities. And we can similarly define another quantity which will be the difference of these two quantities, Tx and Ty, and they form a nonlinear coupled differential equations. So we first linearize these equations in order to derive the condition for the existence of Mpemba effect. And for that, we choose first choose initial conditions which are close to a given final steady state, and we linearize those equations around the final steady state values. So we get a linear time evolutions, and with that we can derive the condition for the existence of the Mpemba effect, where the initial conditions are related to the system parameters by this relation. And using this condition, we choose a pair of initial conditions for the systems P and Q, where P is initially at a higher temperature than Q, and it shows the Mpemba effect and also the inverse Mpemba effect. And here we compare the linearized solution along with the complete solution, and they seem to match very well. The third plot is for the strong Mpemba effect, which shows that the system P can decay exponentially faster compared to system Q. And now the Gaussian approximation for the velocities that we had considered while deriving the time evolution equations is well validated from the results of molecular dynamics simulations So here the dots represent the solutions obtained from the molecular dynamics simulations, and the solid line shows the complete trajectory obtained from the analytics, and they seem to match very well. So I'll quickly summarize what we saw. So first we did an exact analysis for a simple collision model, which is the Maxwell model. And there we showed that for the case of bi-dispersed gas, we can see the existence of Mpemba effect and also the strong Mpemba effect starting from steady state initial conditions, where the initial conditions can be accessed by tuning the system parameters. And in the next study, we show that uh, the presence of anisotropy in the velocity distribution can also lead to the Mpemba effect, where we did kinetic theory analysis based on more realistic collision. So these models can serve as a good candidate for the granular experiments which are still lacking in this field. So these are few of the references where one can analyze, study in detail for these effects. Thank you.
Thank you, Apurba. Are there questions for Apurba?
Sushmita, sometimes the questions are in the chat.
Okay. I didn't see that. Oh, yes. Vani, do you want to just ask your question?
Yes. But generally, what is a protocol? Can we type the questions in chat? Do we disturb? It's not very clear to me. Or do organizers, when we type the questions in chat, do they read them? How does it work?
Yeah, I can read the question.
Yeah.
Okay.
Yeah,
no,
I think
no, this
now
is,
we
this
can
is generic,
you can go ahead and we'll make it clear at the beginning of the talk so that there is no confusion next time.
Yeah. Okay. Thank you. So Apurva, so I just wanted to know, in general, is there any precondition, or does any system shows this Mpemba effect? Can you say a little bit about that?
From analysis, we can say that whenever the quantity of interest that the system poses, like it can be temperature, magnetization, or any other quantity, if it is dependent on certain other parameters, then only we can try to ask the existence of the Mpemba effect, and then we need to choose the initial conditions accordingly.
No, I didn't particularly mean your work, but in general, when regarding Mpemba effect, like you showed water shows and other things. No, is there anything that one can look for in the systems to see whether such an effect can be observed or not?
Yeah, like for other systems also, if you want to measure the temperature as a function of time, and if the temperature is dependent on other quantities, like in the case of water, the time evolution is also monitored by the hydrogen bonding.
Okay.
So in that case, if there is such quantities which also govern the time evolutions of the temperature, then we can ask the existence of the Mpemba effect in such systems.
Okay, thank you.
Like if the temperature evolves monotonically, then we can obviously cannot see the Mpemba effect.
Apurva, I have a short question.
Yeah.
See, in the case of water, as you said, people say hydrogen bond plays some role.
Yeah.
So, what is analogous thing for granular media? I was just thinking, you have the notion of force chains. Do they play any role in explaining this phenomena?
So here in the context of granular media, so suppose we consider the mono-dispersed gas where only one type of particles are there. So in general, due to the presence of inelasticity, the equipartition is not there in the kinetic energies along x and y components here. So the total temperature, so we generally define the total temperature as the sum of these two quantities, Tx and Ty. But then we see that it is also governed by the initial difference between these two components, X and Y.
So now my question was, whenever I hear about granular media, this very nice idea of force chains, some kind of emergent properties keep coming. So I was wondering whether you can explain some of this effect using force chain ideas. Just a very vague thought.
Sorry, sir, I think I do not know about that.
Okay, fine. Thank you.
I will look into that.
We'll thank Apurba again and see you all next week.